In this lab, I want to take a look at a rolling cylinder on cylinder joint. And so I have used the design accelerator to create a couple of gears. And if I check the kinematic motion of this, the smaller pinion gear turns the larger gear, depending on the ratio between the diameters of these two gears. And so then I'll go into dynamic simulation. In dynamic simulation, I use a rolling cylinder on cylinder joint. And we have a choice of adding a tangency, so two constraints, rolling and tangency, or if it's already modeled in position, then we only need one constraint to define the joint. Again, if I drag this, we see that the pinion gear moves the larger spur gear. And if I want to put this into the simulation player, if I right click on the appropriate revolution joint, and I'll go to the properties that it's at, and I'll tell it to do an impose motion, let's say a constant value of 360 degrees per second. And we'll tell this to play then for maybe 5 seconds. If I want to see a graph of the ratio between the RPM or the revolutions per second of this gear versus the revolutions per second of this gear, I can show that on the output grapher. And I started to say RPMs, revolutions per minute. You can also display this in terms of revolution per minute rather than degrees per second. And we'll see that in a later lab. So I'm going to go to the output grapher and I will show the two revolution joints. And so I'm going to select the velocity, display the velocity of 1, and I'll display the velocity of 2. And again, it shows that in units of degrees per second. I'll go ahead and play this. These colors don't match up with the colors of the gear, so I'm going to make some changes here to make that maybe less confusing. I'm going to go to the curve properties of this gear, and this is actually the smaller yellow gear. I'm going to change that to yellow, and then I'll change the curve properties of this one. And yellow might be difficult to see. Let me go back and see if I can find something that might be a little bit easier to see. Thought I might be able to do a shade of yellow that would be easier to see, maybe about like that. And then I'll change the color of this one, so I'll go to the curve property and I'll change this one to blue. Okay, so now when I play this again, so when this one is doing 360 degrees per second, this one is doing a little under 150. If I want to interrogate that, well, we can see here 145.263 degrees per second. So you can see the graph the ratio between those two gears. Now, we're using gears here for the demonstration, but keep in mind, it doesn't have to have these teeth on here. The name of the joint is a rolling cylinder on cylinder. So anytime you have two cylinders in contact where they don't slide against each other, so they roll against each other, then we would use that rolling cylinder on cylinder joint. So even though we have teeth shown on here, you could have an application where there were no teeth, but one roller rolls against another roller. One other thing that you'll notice is if I look at this directly on, we'll see that the teeth interfere a little bit on using the design accelerator to create gear teeth. In a later lab, we'll see how to create some more precise gear teeth, and the way to do that is I would right click on the design accelerator node and tell it to export tooth shape, and then I can get a precise involute curve for the pinion and the gear. But we'll see how to do that later on. I just wanted to point that out now though, because some people are bothered by the visual impact of that interference. The design accelerator creates a cosmetic gear to save computational time rather than a true involute gear. So we have some additional steps to create the true tooth profile. So I'll start a new metric standard millimeter assembly file, and I'll name this rolling cylinder on cylinder joint. And then I'm going to go to the design tab, and I'll go to the spur gear generator, and I'm going to do a pressure angle of 20 degrees, no helix. For the module, I think I'll leave that on 2 for now. For the number of teeth, 23 on the spur gear, 57 on the gear, and base width 20. I'll say okay to these settings. I'll click someplace on the screen, and so we see our two gears. I'll draw drill down to find the smaller pinion gear, and I will open it. I'm going to go ahead and change the color of this gear to yellow. You can use whatever color you like, and I'll start a new sketch on the XY plane. Draw a circle at the origin, and let's dimension that as 15. Now, depending on how you have your screen set up, you might need to hit F7 to see that. And then I'll do a center point rectangle, put it in about like that, and I'll dimension this height as 20, and I'll dimension the width as 8. I'll then do an extrude cut of the circle and the rectangle, and I'm going to tell it to do cut through all. I may need to flip the direction, say OK to that. Now I'm going to turn on the visibility of the pitch diameter of this surface body. So I right clicked on pitch diameter, turned on the visibility of that, and let's see what the diameter of that is. If I go to the sketch and I edit that sketch, I see that this dimension is 46, and that's the variable DA_D. So we need to remember that number 46. Now actually at some point we'll see where we can just use that variable name and we don't have to memorize the number. I'll save this file, and then I'll open up the larger gear. I'll start a new sketch on the XY plane. I'll draw a circle. I'm going to make this circle 45, and I'll do a center point rectangle. I'll dimension that rectangle 60 for the height and 28 for the width. I'll then do extrude. I'll select the rectangle and I'll select the circle. Tell it I want to go through all. I change the color. Set it whatever color you like. I'm going to turn on that pitch diameter surface body. Okay, I want to see what the diameter of that surface is, and I see that it's 114. I'll go back to my assembly. Whenever you see a lightning bolt here, indicates that the assembly needs to be updated. So I'll click on update, and I'm going to turn on the visibility of the Z-axis of the assembly. So make that visible. Make sure that this isn't grounded. So I'll click on that sub-assembly, uncheck grounded, and now I can move these around. And I'm going to turn on the visibility of the axis in the pinion gear, and I'll also turn on the axis in the larger gear. And then I'm going to constrain the axis of the pinion gear to the axis of the assembly. And then I don't want this gear to move back and forth along that axis, so I will find the plane that goes through the back side of this gear, and I'll constrain that flush to the XY plane of the assembly. Alright, then I want to measure the distance from this axis up to this axis. So I'll go to the inspection tab, and I'll measure, and I'm going to set this out to all decimal places, and I'm going to measure from this axis up to this axis, and we see that that's 80 millimeters. Now sometimes that will be a number that isn't rounded off real evenly, in which case we will have to use the variables for the pitch diameters to determine that distance. So 80 millimeters. Let's turn on the visibility of the XZ axis of the assembly, and then I'm going to offset this up 80 millimeters. I then want this axis constrained to that offset plane. So I'll constrain, I'll select this axis, and I'll select this plane, say apply to that, and then I'll constrain the XY plane flush of the assembly to the XY plane of this second gear. Now in this case, the axis could move back and forth along this plane, and so I need to constrain this axis also to the YZ plane. I'll select the YZ plane, and I'll select this axis, and now that axis can't move back and forth along this plane because it's constrained to the YZ plane of the assembly. Now if I try to turn one of these gears, we see that they don't rotate. So this spur gear is a sub-assembly of the main rolling cylinder on cylinder joint assembly. So I need to make that flexible. So I'll right click and I'll do flexible, and now when I drag this, we see that they rotate. So the design accelerator automatically put a rotational motion constraint between these two gears. If I wanted to just drive these, I could do an angle constraint between this plane and of the assembly and a plane going through the pinion gear, and then drive that angle. So let's just go into dynamic simulation, and I'm going to turn off the visibility of these planes. So I'll go to environments, dynamic simulation, and it tells me that the mechanism is is over constrained by 3 degrees, I'll come over here to where it has an I symbol, and it lets me know that that cylindrical joint is redundant. So I need to suppress this constraint, and before we can do that, we have to go to the simulation settings, tell it to uncheck to automatically convert constraints, but I want to keep the constraints that we have, and then I'll just delete this redundant constraint. Let's undo that for a minute. If I come up here and I click on this mechanism status, it gives us a report of the redundancy, and sometimes we can use this to determine how we can eliminate our redundancy, and we'll see in a later lab how to use this table. It isn't always as obvious as the one that is highlighted. Sometimes removing some other joint will get rid of our redundancy. In this case though, it's obvious on this one because we just need the 2 revolution joints. Alright, then I will go to insert joint, and I want a rolling cylinder on cylinder. And again, ignore the fact that there are teeth on this. It could be any 2 cylinders that roll against each other without slipping against each other. And it asks us to select component number 1 and component number 2. Notice it's on 2 constraints rolling in tangency, but we're already set to tangent. Select the edge of the pitch diameter, and then I'll go to cylinder number 2. I'll select the edge of this pitch diameter. And when I say apply to that, it tells me that it's over constrained because I don't need that tangency. These gears were already set tangent to each other. So I'm going to undo that, and I just noticed that we already have a rolling cylinder on cylinder in here. So apparently the current version of Inventor automatically converted the constraints from the assembly environment into a rolling cylinder on cylinder joint. Let's edit that. I'm going to go to edit that, and I see that it did it as 1 constraint rolling, so it did it correctly. I'll go ahead and delete that one, and we'll put it in manually. I'll insert the joint, put it on 1 constraint. I'll select the circle on the edge of this cylinder, and then for second component I'll select a circle on the edge of this cylinder, and I'll say OK to that. And I'm going to delete the one that was put in there automatically, so I'll delete that one. And let's go now to the properties of this, and we see that it automatically picked up the radius of these 2 gears, and so it has determined the ratio between those gears. I don't need to type in the ratio, and that was by selecting this cylinder, the edge of this pitch diameter and the edge of this pitch diameter. It determined the ratio. I'll then find the revolution joint for the pinion gear, and I'll go to properties, and I will enable that constant value. Now we could put in the input grapher, speed it up, slow it down, change direction, 360 degrees per second for my velocity, and I'll play this, say, for 5 seconds. That was rolling cylinder on cylinder. With these pitch diameters, I guess it helps illustrate that we don't really need these teeth on here, because we selected these 2 cylinders. They roll against each other, they don't slide against each other.